Let's say I wanted to determine whether or not the following limit exists, and if it exists, what it's equal to. Limit, new pens, by the way, yeah, new pen time. You guys are in for a treat. You can see what I'm writing on the board with these new wonderfully inked up black pens. All right, I know it's not that exciting, but it's exciting to me. In this world, that's what passes for excitement. So let's find the limit is x, y goes to 0, 0 of 8x squared y divided by x to the fourth plus 3y squared. And so here are the paths that we typically go to. My first choice usually is either y equal to 0 or x equal to 0. And basically, if I'm saying it for y, you can also say it for x, right? If you're saying y could equal something in terms of x, you can say x is equal to the same sort of thing in terms of y. So that's a typical choice. Usually only one of those, because often if you do both of them, one of them ends up not existing, or more commonly than both of them give you the same thing. Y equals x is a super common choice. Y equals x to a power, or x equals y to a power. Power can be positive or negative. I should also say y equal to x. More generally, we often pick y equal to a multiple of x, or x equal to a multiple of y. What else? I feel like I'm missing something here that is pretty standard. Maybe not. Maybe these are like our usual. I feel like, yeah, I guess you could also multiply this by, right? You could do y equal to a multiple of x to the power. So you could do y equal to k times x to the power, or x equal to y times k to a power. There obviously are other choices, right? There's literally lots and lots, infinite numbers of paths that go through the origin. I guess I should point out, right, these powers don't have to be integers, right? Those powers can be any real number. So you could have like a cube root. You'd have to be a little bit careful when you're talking about square roots, right? Typically, you want to think about being able to come out from any direction. And so if you use a square root, you can't have x being negative. So typically, we kind of try and limit ourselves to things where no matter what types of values you're plugging in for x or y, you're still defined. But these are kind of the most common choices for paths that we try to utilize, typically to show that the limit does not exist. So if I was trying to show that the limit did not exist, or if I was trying to find the limit or show it doesn't exist, I would start by trying some paths, even if I thought the limit existed. I don't see anything factoring nicely here, so I'm pretty sure it's probably not going to exist, but I don't actually know. So I'm going to start by letting y equal 0. That seems reasonable. It might not get me anything though. So I do y equal to 0, I get the limit. So y is 0, so I'm just left with x. So the limit is x goes to 0 of 8 times x squared times 0, so 0 on top, right, over x to the fourth plus 0. Okay, 0 divided by not 0 is the limit as x goes to 0 of 0, and the limit of a constant is the constant. So in one direction, the limit is 0. Now I will just say, right, if I let x equal to 0, I would get the same result. So if x equals 0, you get 0 on top, and you get 3y squared on the bottom, and the limit is y goes to 0 of 0 over 3y squared is the limit of 0, which is 0. So typically, not always, but typically, both of these usually both result in it being 0 and usually are the same. So let's try something else. Because again, our thought at least is that the limit probably doesn't exist. That should be kind of your base assumption for most of these limits. 9 times out of 10, the limit's not going to exist. So let's do the limit as, oh, so sorry, I have to pick a path. Pick a path of pickled peppers? No, pick a peck of pickled peppers, which is what Peter Piper picked. Okay, so let's let y equal x. That's usually my next go-to, right? This is kind of the order I try things in. I try y equals 0, x equals 0. I try y equals x. If they're still the same, then I might try like y equals x squared or y equals x cubed or something like that. So let's try y equals x. If I do that, I get the limit as x goes to 0. I'm usually writing x as if I have the choice. So y equals x is going to be 8 times x squared times x. So 8x cubed divided by x to the 4th plus 3x squared. So this is looking like a 0 over 0. Here's what you're going to want to do. I typically decide to divide everything by the lowest power of x, right? So if you're going to infinity, you want to divide everything by the highest power of x in the denominator. If you're going to 0, you typically want to divide everything by the lowest power of x that you have. So if you divide everything by x squared, I guess you can just factor x squared on the bottom as well. If you divide everything by x squared, you're going to get 8x over x squared plus 1. And now we can actually evaluate that, right? We can plug in the 0, and you get 0 over 0 plus 1. Okay, still 0. Doesn't mean that this, so that doesn't mean the limit is 0. It just means we haven't shown it doesn't exist yet. It means the limit could be 0, or it could be something else, or it could be, sorry. So basically, once we've got 0 once, the limit either has to be 0 or it has to not exist, right? Because if we get everything being 0 and then 0, if we get something else, the limit's not going to exist. So let's try. So my usual thought for this is I'm often trying to make a choice that's going to have the degree, if it's a rational function or a rational-ish type expression, I'm usually trying to make a choice that's going to let the top and the bottom both have the same degree, meaning the same highest power. If I let y equal x squared, I'm going to get x to the 4th on top, and I'm going to get x to the 4th on the bottom. So that's usually the choice I'm trying to make. That's usually the choice that makes things work out. So that y equal x squared, we're going to get the limit as x goes to 0 of 8x squared times x squared is x to the 4th over x to the 4th plus 3x squared squared is 3x to the 4th. But this is just 8x to the 4th over 4x to the 4th. I feel like I might have done this already. It's all right. And 8 over 4 is 2, and x to the 4th over x to the 4th cancels. This is the limit of 2, which is 2. And then we can say, oh, this limit does not exist. Because we found 2 different paths that go through the point we're approaching where the limit has a different value. So that means the limit doesn't exist. Stop me if you have questions. Yeah. Another option that definitely I saw in Waldron, one of Waldron's homework, there's like one homework problem where this is presented as an option. You can also use polar coordinates. So I don't remember if we spent much time in 21B talking about polar coordinates or not. The basic idea is that, right, you're taking your usual XY coordinates and writing it in terms of a radius r and an angle theta measured from the positive x-axis. So, right, we know that cosine of theta is x over r, so that x equals r cosine theta, and sine of theta is y over r, so that y equals r sine theta. And importantly, this is usually the tip off that you might try polar coordinates. X squared plus y squared equals r squared. So what I'm trying to say is that if you see an x squared plus y squared, it's not a bad thought, at least, to say, maybe I should try polar coordinates. There's one other thing to say, but I'll get there in a minute. So I want to try looking at the limit as x comma y goes to 0 of, what have I got here? 3y squared x over x squared plus y squared, which, as my previous example was, is a 0 over, sorry, you can't see that, is a 0 over 0 type of limit, right? If you actually just plug in the 0 and the 0, you get 0, which is indeterminate, which means you have to do stuff. So let me cycle through my pens here so I don't use up all of this one at once. Right. So one other thing we need to note is that if x and y are both going to 0, well, then r is also going to 0. But theta can be anything, right? If the radius is 0, it doesn't matter if you're going around this way or this way, how much, right? If your radius is 0, your angle doesn't matter. But it does matter in helping us determine the limit. So let's try using, let's try using polar coordinates to see what happens. So I'm going to replace every x squared plus y squared with r squared, and every individual x and y with r sine theta and r cosine theta respectively. X is r cosine theta, y is r sine theta. So I'm going to rewrite this as the limit as r goes to 0 of 3 times r squared sine squared theta times r cosine theta divided by r squared. The r squareds cancel. So this equals the limit as r goes to 0 of 3 sine squared theta times r cosine theta. And even though theta can be anything, we're going to get that r is going to 0. This is going to be 0, which means this limit exists, right? We just showed that it doesn't matter what path you took, right? Because the whole kind of point, right, again, if you're approaching 0, 0, is you can come at it from any path. Well, if you're saying theta can be anything, you're kind of accounting for the idea that you can come at it from any direction, which is kind of neat. Another way, so this is kind of if you're trying to show a limit actually exists. So let's pretend like we hadn't done this. Let's go back for a second and say, like, let's say we had this problem. And then I'm going to have to ask you a question. So let's say we were doing the limit, that same limit as xy goes to 0, 0 of 3y squared x plus, 3y squared x over x squared plus y squared. So let's say we tried some patterns, right? Like if we tried, I think it's, I mean, obviously all the answers are going to be 0 because the limit is 0. But if we tried y equal to 0, we have 0 over x squared, going to be 0. If we tried x equal to 0, we have 0 over y squared, going to be 0. If we tried like y equal to x, we would have the limit as x goes to 0 of 3x cubed over x squared plus x squared. And that's going to be the limit of 3x over 2, which is going to go to 0. Or we could try something, I mean, it's going to be kind of stupid for me to keep doing this because I know the limit's 0. But what I'm trying to emphasize here is that doing as many of these as you can is never enough, right? I could do 20 different paths. They could all be 0. That doesn't mean the limit, doesn't mean we've proved that the limit is 0. It just means we think it's 0, but we haven't found a path where it's not. Just because you haven't found a path where it isn't doesn't mean there doesn't exist one until you've actually shown the limit is 0 or whatever the value is. I mean, we could try y equals x squared. If we did that, we'd have the limit. Let me do x equals y squared. Actually, that seems more interesting. We did x equal to y squared. We have the limit as y goes to 0. Actually, replacing the x's with y squared of 3y squared times y squared, so 3y to the 4th over x is y squared. So I've got, this seems like it's going to be wrong. I'm a little intrigued about what's about to happen here. Oh no, I see that. I was convincing myself I was going to be wrong. So y squared squared is y to the 4th, and then y squared is y squared. I thought that was going to be a y to the 4th for a second. I was like, this is right. So then divide everything by the lowest power of y. If you divide everything by the highest power of y, you get 3 over 1 plus 1 over y squared. That's not good. I mean, it'll still, you can kind of justify that that's 0, because 1 over 0 goes to infinity, and then 3 over infinity goes to 0. But that's not the nice way to do it. You should divide everything by the lowest power of y. And then you get 3y squared over y squared plus 1, which goes to 0 over 1, which is 0. So yeah, we're pretty well convinced here that the limit of this is 0. So if we didn't know how to do this with the polar coordinates, how would we do it? Well, and this is where I actually have to ask you guys. In your classes, is your professor having you actually prove that limits are equal to what they're equal to? And you actually need a response. You don't think so? Okay. All right, cool. Well, let me show you this one, because this one is not like super hard, still kind of gets at the idea. So let me show you how to so really, I would say if I had to do this one, I would if I thought a limit existed, I would first explore the option of, can I make it polar? And I would give that a try, because that's often a good plan of attack. So if you think a limit exists and it seems like it would lend itself nicely to polar coordinates, that's an option. At least if you're going through the point 0, 0. Other points, not really an option. But there is another way to do this one specifically. So I'm going to talk briefly about this just to remind everybody of some stuff. So back in 21A, you hopefully saw delta epsilon proofs. I know they're probably not anyone's favorites, but the delta epsilon proof said, right, if basically, I should back up 1 sec. It said, right, it said something like, and I'll give an actual example. The limit as x approaches 2 of, I don't know, 3x minus 1 is equal to 5. And the way we would prove that would be by showing if x is close to 2, which we write like that, if the difference between x and 2 is less than a small number, then the function is close to 5, the limit. That's how we write that. The difference between the function and the limit is small. Okay, so that's the idea with limits in 2 dimensions. You show that if x is close enough to the thing that x is approaching, the function has to be close to the limit value. And that's when you're talking about x approaching 2. So the thing about this is x can only approach 2 from one side or the other, right? So you're kind of on the left of 2 or on the right of 2. Whereas if you're approaching a point, right, if xy is approaching 0, 0, you can come at it from like any direction around 0, 0. So you're not just saying like the difference between your thing and the point it's approaching is smaller than some number. You have to say like the distance between them is less than some number. Meaning, what I'm trying to say is that what we're trying to say here in these multivariable situations is to show that the limit as x, y approaches 0, 0 of, what did I say the function was? 3x squared y over x squared plus y squared is equal to 0. So to show this, what we have to do is the same thing. We have to show that if our point, if our variable is close to our point, okay, so if the distance between them is small, so if the distance between x, y, and 0, 0 is small and also positive. Same thing here, this should be positive. So if the distance between them is small, then the difference between the function and the limit is also small. I'm sorry, I forgot the minus 0. And normally this can be a giant pain in the butt. For this particular problem, it's not that bad. Graphically, here's the idea. We're trying to show that, right? So basically, you've got some circles worth of points, right? So how do I want to say this? So right, here's a circle of radius delta. And you're trying to say that your XY coordinate, which maybe is like, I don't know, right here, that the distance, right, this value here is less than that value there. Where this height is the absolute value of Y, and this length is the absolute value of X. Okay, so that's the idea. So what we want is this. So basically we kind of start with what we want and we work backwards. And now here's the key observation of this particular problem. I've got 3x squared y over x squared plus y squared in absolute value. And here's what you want to notice. And this isn't something that's hard to believe once you see it. X squared over x squared plus y squared is less than or equal to 1. It's got to be, right? The denominator is definitely bigger than or equal to x squared, right? X squared is definitely less than or equal to x squared plus y squared. So when you divide them both by x squared plus y squared, you get 1. So then we want this to be true. Remember, we're trying to show that the function is close to the limit. But then what we can say is, well, I know if this is true, I can say that this is true if this is true. Sorry, I'm kind of trying to make a mess of this here. I can say that this part here, well, that's less than or equal to 1. So this has got to be less than or equal to 3y. So if that's less than epsilon, then we're good to go. But look, I can also say, sorry, I keep kind of erasing this. It also should be, I don't know if clear is the right word. It shouldn't be too hard to believe that whatever the absolute value of y is, it's definitely less than delta, right? If your point xy is within this circle of radius delta, then the biggest y can be is delta. So look, we've shown that delta needs to be equal to epsilon over 3. And so I'm not going to say too much more here, but basically the idea here is that if delta is epsilon over 3, then if your point is within epsilon over 3 of the origin, then it is true that your function is within epsilon of the value 0, which is its limit. So nobody loves this, right? This seems like a giant pain. But some teachers do really kind of focus on showing that limits are equal to what they're equal to. This is the delta epsilon way of doing it. It's kind of a pain, just like it was a pain back in 21A. But this is kind of the idea, right? You're saying that if your point xy is close to the point it's approaching, 0, 0, how close? Delta close. Then your function, 3x squared y over x squared plus y squared, has to be close to the limiting value, 0. How close? Epsilon close. But I won't do any more of that unless you guys specifically say, oh, James, we actually do need to do more of that. There's some other questions. But so if you want to see more of this sometime, let me know. Otherwise, I'm just going to kind of leave it there. But if you do have questions about this, I can definitely do other examples another time. Or you can come see me in office hours after class, and I can do examples there. They're kind of a pain. They all rely on this idea of, just like with 21A, right? Starting with the thing you want to be true and working backwards until you get a condition on the thing that you need to be true. Yeah. Yeah. Okay. So let me go back here for 1 second. Yeah, not that. Yeah, there's another example that we could do. Let's look at one more example. Let's look at the limit. Maybe not just one. We can do more limits if you guys want. But they're kind of important. The limit is xy goes to 0, 0 of 4xy over x squared plus y squared. I guess they're important because someone might ask you, like, how, or I guess in the previous example, let me go back for just 1 second. So in this example, someone might say, well, I've got this function, f of xy equal to what it was, 3y squared x, or I would write it as 3xy squared over x squared plus y squared. This function is definitely not continuous everywhere because it's undefined, right? It's clearly undefined at 0, 0. But someone could ask the question, okay, well, if it's equal to that when xy is not 0, 0, could you define this to be equal to something at the point 0, 0 that would make it continuous? And the answer for this function is yes, because the limit exists. You could say, oh, I'm going to define this to be equal to 0, which is what the limit is. And then this function is continuous everywhere. Because whatever point you're at, the limit is equal to the function value, right? That's the whole, right? Continuity in more dimensions is still the same idea. That for a function to be continuous at a particular point, the function value and the limit as you approach that value have to be the same. It's just that in this kind of example, the limit can come from any direction, which is funky. I almost got red pen on my face. That'd be great. Okay. Anyway, so this one you could totally define, right? You could just kind of like how in 21a, you could say, okay, can you define the function f of x equal to sine of x over x? Is there something you can define it to be when x is equal to 0 so that it's continuous? And the answer is yes, because we know the limit as x goes to 0, sine x over x is equal to 1. So if you define the function to be equal to 1 when x is equal to 0, then you've made a continuous function. It's called a point discontinuity, right? When you're missing just one point, you can put it back in and make it continuous. That's what kind of the idea is here. Whereas here, the limit doesn't exist. Let's pick some paths and see if we can make it not exist. So I'm going to pick y equal to 0, right? That seems like a good choice. Y equals 0, you get the limit is x, y, sorry, is x goes to 0 of 0 over x squared, which is totally 0. If you pick y equal to x, yeah, right, this one's going to be, that's going to be 2. You get the limit as x goes to 0 of 4x squared over x squared plus x squared. But it is also possible to use polar coordinates to see that the limit does not exist. Let me show you what I mean. Yeah. So if instead I use polar, I'd say, okay, I'm going to rewrite this as the limit as r goes to 0 of 4 times x is r cosine theta, y is r sine theta, x plus y squared is r squared. But look what happens here. The r's all cancel. So you've got the limit as r goes to 0 of 4 cosine theta sine theta. And the problem here is that theta can be anything. So, I mean, r going to 0, right, means that the limit actually is 4 cosine theta sine theta. But since there isn't any restriction on what theta can be, this can be anything. And since it can be any value, that means it's not one particular value, which means the limit does not exist. So, right, if you end up with something where you still have thetas in it, and you're doing polar coordinates, the limit does not exist because you can't say what it's equal to specifically. Okay. I think I've said enough about limits, unless you want me to say more. I will just point out that oh gosh, there were words I was going to say. Most of the time we're going through the point 0, 0. most of the time, if we're going through 0, 0, it's going to not exist. But not all the time. Sometimes it's going to exist. Sometimes you're going to factor stuff and cancel. Sometimes other things are going to happen. Well, let's go ahead and look at partial derivatives. Yeah. So partial derivatives, in one sense, are super duper easy because, and I think I said this last class, or maybe I wrote an email to someone. With partial derivatives, you're literally treating whatever variables you're not differentiating with respect to as constants. So let me kind of break it down. Let me break it down. Sorry, I'm thinking of like an old song. Break it down. Partial derivatives. So this is kind of my favorite example because it's not too terrible to draw. We'll see. We'll see how that goes now that I've said it. So let's look at the function of two variables x, y equal to 9 minus x squared minus y squared, which is a downward opening paraboloid, right? It's like a parabola but rotated around the z-axis. So here this is, and I'm going to try and do a pretty good job of drawing this because we're going to use this drawing. Let's see here. So let me see. Yeah. Let me start with that. So let's say here's 9. Let's say here's 3. We're going to go down this way. And yes, I know that the parabola does continue on further, but I'm going to try and draw this. So I'm going to stop there. And let's go this way as well. And what I'm really kind of interested in is I'm going to investigate what's happening at the point 1, 2, 4. Yeah, 1, 2, 4. Right? If x is 1 and y is 2, then z is 4. So I'm going to go this way. Right? So we are going 1 in the x direction, 2 in the y direction, and then 4 in the z direction. So I'm going to try and get this to be about right. So let's say that's about 4. Yeah, that seems about right. Then I'm going that much up from there. Okay. So I'm going to draw the level curve. Let's see if I can do this. Okay. Oh, that's pretty good. If I do say so myself. So what I've drawn there is the curve when z is equal to 4. So when z is equal to 4, or when the function's equal, right? Often we think, just like say y equals f of x, we say z equals f of x, y. So z is equal to 4, where we've got the equation 4 equals 9 minus x squared minus y squared, which becomes x squared plus y squared equal to 5. So it's not surprising that, right, it's a circle with radius square root of 5. And then, let me erase some of this stuff. I don't need quite all of this down here. What I want to do is I want to look at, and then there's, sorry, I know this is getting a little bit. So here's the line in the xy plane, x equal to 1. And here's the line in the xy plane, y equal to 2. What I want to actually look at is the slice of this surface through the point, through the plane, I should say, y equal to 2. So if I set y equal to 2, I'm going to get, well, in fact, if I set y equal to 2, right? If I set y equal to 2, I'm going to get the equation z equal to 9 minus x squared minus 4, which is z equal to 5 minus x squared. So it's no longer a downward opening parabola, just not quite as high. I should use a different color. I got colors. Why am I using all black? Sorry, Julian. I just saw you there, and I'll read your comment in just 1 second. But let me draw this. So that doesn't look the best. But you guys can kind of see it's a. Oh man. It's supposed to be a straight parabola, but it does not look super duper straight. I'm not pleased with that parabola. Let me try and fix it. Sorry, I want it to look good so you guys can really see what's happening here. Let me try it. I think I know. I think my point is a little bit off. Sorry, 1 sec. I think I kind of overshot there. That should make it a little bit better. Okay. Sorry, I'm trying to make it look good. There we go. I think that's a little bit better. Okay, I think that looks a little bit better. I'm trying to fix this. Yeah, okay. Right there. There. All right. So variable isn't included in the function. Does that always mean that the function is equal to that missing variable? Do you mean what Julian? Are you specifically talking about like I'm replacing z with f of x y? Is that what you're referring to?
Yeah, like when z isn't like included in the function.
Kind of. Specifically,
or is it because you did like the point? Is that why the?
No, it's more that if you have a function of x and y, we usually think of that function being in terms of z, being as z. Just like if I wrote the function f of x equals x squared, we often make the default choice and be like, oh, that's y equals x squared. But if you have a function of more, like if you had a function f of x, y, z equal to the square root of x squared plus y squared plus z squared, we wouldn't like say that it was z equal to that. We would say it's just a function of x, y, and z. So it only really works if it's a function of x and y.
Okay, got you. Thank you.
So sorry, 1 sec. Yeah. Okay, sorry. So the idea here is that on this red curve here, that's on this surface, right? So this red parabola, which I guess I could write, right? This red parabola, z equal to 5 minus x squared in the plane y equal to 2, right? For one, I can even, right, there's the plane, y equal to 2. So really, this parabola here, which doesn't include all the stuff I just shaded in, this parabola is the intersection of the surface 9 minus x squared minus y squared and the plane y equal to 2. But what's interesting is that, I should erase this because we don't really need this, is that if you look at this parabola here, sorry, I'm erasing my beautiful picture. If you look at this parabola here, it lies on this surface and definitely intersects, right, the point 1, 2, 4. We can ask, how is the function f of x, y equal to 9 minus x squared minus y squared changing if we move in the direction of x? So basically I'm asking, what's the slope of the tangent line if we move forwards, right? If I think of this as like a hill, right? And I'm standing at this point on the hill and I face in the positive x direction, so forward. If I walk along that red parabola from this point forward, I'm going to be walking downhill because the slope of my tangent line there, well, I can find the slope of the tangent line, right? If this is my curve when y is equal to 2, then I can find, and there's like a million different ways you can write this. You can write it as del f del x, or you can write it as f subscript x, or I could also use a z because I'm calling the function z, right? All of these mean the partial derivative with respect to x. I can see that that's equal to, well, the derivative of this is negative 2x. And I could have looked at it here, or I could have looked at it here. The derivative of this function with respect to x is negative 2x. The derivative of this function with respect to x is negative 2x, because the derivative of 9 is 0. And if you're holding y constant, y isn't changing. And if something isn't changing, its derivative is a big 0. So that's how partial derivatives really kind of work. We say, oh, we're thinking of this thing being constant and this other thing changing. So from this point here, if I'm traveling in the x direction, the derivative is negative 2x. And at this particular point, 1, 2, 4, if I plug in the point 1, 2, 4, well, I'm just plugging in 1 for x. So this partial derivative, del f del x, evaluated at the point 1, 2, 4, sorry, I know it's a little bit messy there, is equal to negative 2 times 1, which is negative 2. On the other hand, if I were to hold x constant, do I have enough room? Maybe. Sure, let's hold x constant. So again, we're at this point 1, 2, 4. So that means now we're holding x equal to 1, and we're going to get z equal to 9 minus 1 minus y squared. So through this point here, I think I can do it. It's always a challenge. I want to be up this way. Problem is I can't see. I need that. That's what I need. Okay, there we go. Okay, that's not the best, but again, hopefully you guys get the idea there. Right, like I'm traveling right from this point. If I travel in the positive y direction, the derivative is going to be, well, again, the partial with respect to y is going to be negative 2y. And it's going to be at this particular point, negative 4. So if I'm at this point on the hill, if I travel forward, my slope isn't as negatively steep as if I travel to the side. Right? Traveling forward, my slope is negative 2. Traveling to the side, my slope is negative 4. Kind of interesting. Yeah. So that's some of the idea here. But what I should also say, so we can take lots of derivatives, right? So yes, this is nice. It's good to think visually about what these things mean, right? Like a partial derivative just means if you're on a surface, you're only traveling in the direction of the derivative you're taking. So you're either traveling, if you're taking the partial with respect to x, you're traveling in the positive x direction. If you're taking the partial with respect to y, you're traveling in the positive y direction. So partial with respect to x, you're traveling forward and you're asking what's happening as I move in the forward direction along this curve. Oh, from here, I'm going downwards. Or what happens as I move, if I'm asking what the partial with respect to y is, what happens as I'm moving in the rightward direction, because that's the positive y direction. And in that case, it's still also a negative. But you don't have to have this visual to kind of be able to take partial derivatives. So still using the same function. If our function f of x, y is equal to 9 minus x squared minus y squared. We can take all sorts of partial derivatives. We can take, again, the first partial with respect to x. Again, everything that doesn't have an x is a constant. Derivative of 9 is 0. Derivative of negative x squared is negative 2x. Derivative of y squared is 0. Partial with respect to y. Same deal. 0, 0, negative 2y. You can also take second partial derivatives, right? You can take the second partial of the function del squared f del f squared, sorry, del squared f del x squared, which just like regular second derivatives is just the derivative of the derivative. So this is just del x of del f del x, right? The letter is del, not d, right? So like a curly d. So that's negative 2x. So we're doing the partial with respect to x of negative 2x, which is negative 2. And in a similar way, the second partial with respect to y, del squared f del y squared, would also be negative 2. Coincidence that they happen to be the same. And they're the same because of the symmetry in x and y, right? They're kind of the same. If you interchange x and y, it would still be the same function. So we would expect for the second derivatives to be essentially the same. This just means that in the x direction or in the y direction, the function is concave down, right? The second derivative being negative means it's concave down. And then there's also the mixed partial, or I should say the mixed second partial. So the mixed second partial, there's two of them, del squared f del x del y, and del squared f del y del x. So del squared f del x del y means first you do the partial with respect to y, then with x, right? You write this as del x of del f del y. So first you do del f del y, which is negative 2y. So it's going to be the partial with respect to x of negative 2y. But that's just 0 because the derivative of this, there's no x's in there. This is a constant as far as that variable is concerned. 0. Similar thing is going to happen here. You're going to get del y of del f del x, which is going to be del y of negative 2x, which is also going to be 0. Most of the time, I don't remember what the word is. Most of the time, your mixed partials in either direction are going to, in either order, are going to be the same. There's, oh gosh, I don't. There is some condition of what this actually means. I don't know what the words are. I'll look it up. So the next time, but there is kind of an interesting thing about this. The mixed partial, I don't know if I have a very good interpretation of. I guess what it so I'm reading Grant's notes, big surprise. What you can kind of think of it is if you're at the point 1, 2, 4, and you're facing the positive x direction. If you then move in the y direction, your slope is going to change. It's not change, right? Right? Because I'm saying the derivative in the y direction of the derivative in the x direction is 0. So if I'm looking at the derivative in the x direction, which is negative 2, if I then move in the y direction, my derivative in the x direction doesn't change. And it's true, right? Whether I'm here or if I've moved to being like up here, no, sorry, I know my picture is kind of falling apart. But with whether I'm here or I've moved up here purely in the y direction, my derivative in the x direction is still negative 2. Because if I haven't changed my x coordinate, I'm not at the point like, 1 comma some smaller value of y, some bigger value of z. But if I'm asking what the derivative in the x direction is at the point 117, well, the derivative in the x direction is still negative 2x. If I plug in 1, it's still going to be a negative 2. So that's what the mixed partial being 0 means. It means that if you do the derivative in one of the two directions, in the x direction, and then move in the y direction, that derivative in the x direction doesn't change no matter how far left or right you move in the y direction. Again, geometrical interpretation here, not super duper important, but it is good to have an awareness of. But the real point is that basically the variable you're differentiating with respect to is the only variable, and everything else is a constant. My friend's son is also taking 21C. He's taking the class at the community college, and he was like, "Is it really like? It seems like it should be harder than this, right? For partial derivatives, is it really just as easy as you treat the variable like a constant that you're not differentiating with respect to?" And the answer, we were all like, "Yes, that's totally the answer. You just pretend that y is a constant if you're doing the derivative with respect to x, and vice versa." So, right, if my function, for example, is x to the fourth plus y cubed plus x squared y to the fifth, we can do all the partials. And so oftentimes when they ask you a question, they'll be like, find all the first and second partials, including the mixed partial. Meaning there are 5, technically 6 things to find. I prefer, so this notation is fine, del f del x, but there's a lot less writing to write fx. And we do just say fx, we do not say f sub x or f of x, it is fx. I suppose you could say sub x, but you don't. So I'm going to use this notation. Oh, there is something terrible though, and this is something you should be aware of, is that the mixed partial, del squared f, del x, del y, this notation means you do the derivative with respect to y first, and the derivative with respect to x second. Which is what this notation means. You do the y first, you do the x second. So this notation and this notation have their orders interchanged. This means y first, x second. This means y first, x second. So just be aware of that. Now, what's nice is that for the mixed partial, it usually doesn't matter because most of the time they do end up being the same. But someone could ask you to do like like f, x, x, y. And then you do y first and then x, which would be the same as del cubed f del y del x squared. Kind of silly. Right, so this says you partial respect to x, then x again, and then y. This says x, then x again, then y. So yeah, order is unfortunately opposite if you write it in the other notation. Let's go ahead and look at this example. So I want to find the partial respect to x. So the derivative of x to the fourth, 4x cubed. The derivative of y cubed, with respect to x, the derivative is 0. Basically, if you don't have any x's, you're a constant. Your derivative is 0. Derivative of x squared times y to the fifth. So the y to the fifth we're going to treat as a constant multiple. So the derivative of x squared times y to the fifth is 2x times y to the fifth. And that's it. Let's find the partial with respect to y. Fy is going to be 3y squared plus x squared times 5y to the fourth. How not exciting. I would, if I had to find the second partial, definitely simplify things. So I would probably take a second and rewrite this as, as not dropping the pen, as 4x cubed plus 2xy to the fifth. And this is 3y squared plus 5x squared y to the fourth. So let's find the other things. Let's find fxx. So fxx, I'm going to take the partial with respect to x and differentiate with respect to x again. So the derivative of 4x cubed is 12x squared. The derivative of 2xy to the fifth is going to be 2y to the fifth. X to the derivative of 2x is just 2. Why did y cubed change to 0? Good question, because we are differentiating with respect to x. So again, right, we're in this situation, right, where we're saying, okay, I'm treating y like a constant. So if I'm differentiating with respect to x, or I'm only moving the x direction, the derivative is going to be negative 2x here, and the derivative of y squared is 0, because we're only thinking about moving in the x direction. Y, for lack of a better phrase, is acting like a constant. Literally is a constant, right? If you're moving in the x direction, y is not changing. And again, I'm going to say this a lot. If something isn't changing, if something is constant, its derivative is 0. Right? If you're not changing, and your derivative is 0. Your rate of change is 0. Maybe a better way of saying that. So if I'm differentiating just with respect to x here, well, that's not changing, and its derivative is 0. So then same kind of deal here. Here's the function I'm now differentiating with respect to x again. I'm getting 12x squared plus the derivative of 2x is 2, and the constant multiple of y to the 5th just sticks around. And then we can also find fyy. So the partial of this with respect to y is going to be 6y plus the 5x squared is a constant that hangs around. The derivative of y to the 4th is 4y cubed. So constant multiples, just like with regular stuff, sticks around. Constants on their own get annihilated. Their derivative is 0. So I would rewrite this as 6y plus 20x squared y cubed. Just to do one more partial with respect to x here. If I did f(x)(x), right, the third partial of this function with respect to x, I would get 24x plus 0, because the derivative of 2y to the 5th would be 0. Well, let's find the next partials. So let's find f(x)(y). So again, this means you do the partial with respect to x first and then y second. So you can literally rewrite it as fx y, like that. Fx is right here. It's 4x cubed plus 2xy to the 5th. The derivative of this with respect to y, what's the derivative of 4x cubed with respect to y? Like, oh, he wants me to say, yeah, exactly. Thank you. 2xy to the 5th. So now the x is treated like a constant. So the 2x hangs around. And you multiply by the derivative of y to the 5th, which is 5y to the 4th. So you get plus 2x times 5y to the 4th, which ends up being 10xy to the 4th. Let's find fyx. So fyx is, we're going to take now the partial with respect to y and differentiate it with respect to x. The derivative of 3y squared with respect to x is 0. The derivative of x squared times y to the times 5y to the 4th with respect to x is 2x times the constant 5y to the 4th, which is 10xy to the 4th. And not surprisingly to me, because I've seen this a lot of times, the mixed partials in either order are the same as each other. If you're dealing with a normal function, like anything that's defined is just like x's and y's tossed together, and it doesn't like, there's not some weird like piecewise kind of like it's this when it's this and it's this and it's that. If your function is just like x's and y's and nothing's like on this domain, not on that domain, you should expect the mixed partial in either order should always be the same. There are times when it's different. They're kind of funky. They're really funky, actually. Oh yeah, that's what it's called. It's called Claru's theorem. It is this. So Claru's theorem, which now I'm going to look up real quick because why not? Now, okay, give me the Wikipedia page. Okay, so here's what Claru's theorem says, in case you're curious. If the mixed partials are both defined and continuous in a region containing the point. Oh yeah, so the mixed partials are defined and continuous, then they're equal to each other. I feel like there's more to it than that, but that's what the first thing I clicked on told me. Was Wikipedia tell me. Yeah. Claru's theorem. Yeah, okay, I don't know. Anyway, there might be more to say about that later. It's probably not super important. But there are, so the kind of result is that there are some functions that are not continuous at a particular point. And then you can see for those, like some of those functions, that you can kind of make up something a little bit wacky where the mixed partial one way is not equal to the mixed partial the other way. And I know I've got an example of that somewhere. It's also not the most important thing in the world. But yeah, maybe we'll talk about that at some point. So let's do one more example. What time is it? Okay, we got 15-ish minutes. Yeah. I think having office hours, so I know the problem is. The problem is in the online world, there isn't really like a 10-minute break. Right? Like normally in the real at UC Davis world, class would end at 3, and then office hours would start at 3:10. But in the online world, office hours kind of start right at 3. So yeah. Anyway, that's I should just maybe be more clear next quarter that we're using the UC Davis 10 minutes before and after usual stuff. It's just that there are some freshmen who have never been on campus and they're like, what? Things don't start at 3, they start at 3:10? That can't be true. But it is true. Well, at least it was true. Let's look at this function of x and y. X over x plus y. Let's find all the things. So let's find the partial fx. Okay. Bottom times the derivative of the top minus the top. What's the derivative of the bottom? 1. The derivative of x plus y with respect to x is just 1 plus 0 over the bottom squared. Simplifying, because we are going to take a second derivative here. X plus y minus x is just y over x plus y squared. Okay, that doesn't seem too awful. Let's find the partial with respect to y. So again, that's going to be the bottom times the derivative of the top, which is 0, minus the top, times the derivative of the bottom, which is 1, right? 0 plus 1, divided by the bottom squared, which is equal to negative x over x plus y 1 squared. We can find some second partials. Find fxx. So we're going to take this, differentiate with respect to x again. And I would probably still use the quotient rule, even though you could. No, maybe I wouldn't. I would maybe write this as y times x plus y to the negative second and take the partial of that. So again, partial with respect to x. So it's the derivative of the first thing. Derivative of y is 0 times the second thing. I don't really need to write times the second thing because 0 times anything is 0. Plus y times the derivative of this is negative 2 times my stuff to the negative third power times the derivative of my stuff is 1 plus 0. So this ends up being negative 2y over x plus y cubed. All right. Fyy would be the same sort of thing. This is negative x times x plus y squared. Sorry, x plus y to the negative second. I take the derivative of that. So again, the derivative of negative x is 0. I should say the derivative of negative x with respect to y is 0. So you can make 0 times your stuff plus negative x times the derivative of your stuff, which is negative 2 times x plus y to the negative third, times the derivative of x plus y, which is 0 plus 1. So I end up with positive 2x over x plus y cubed. All right, let's take these first derivatives and check out the mixed partials. They should be the same. It's nice to check though. It's kind of, it seems very satisfying. So they're like, oh yeah, it's the same either way. You should still be careful about making sure that you differentiate things in the order that you were intended to, even if you know they're going to end up being the same. So here's our Fy. Our Fy was negative x times x plus y to the negative second. And our Fx was positive y? Yeah, positive y times x plus y to the negative second. So Fyx, partial with respect to y first and then x second. So it's going to be the derivative of negative x times this stuff left alone plus negative x times the derivative of this with respect to x, which is going to be negative 2 times x plus y to the negative third, excuse me, times 1. Can we simplify that? Sure. Sorry, there's something in my way here. Not that I really need the help, but let's, okay, fine. I guess sure. Do I need to simplify this? No. Am I going to? Yes. Negative 1 over x plus y squared, minus minus, so plus 2x over x plus y cubed. And really I should multiply this by x plus y over x plus y. I really should have just used the quotient rule. Oh well. To get negative x minus y plus 2x. Negative x plus 2x is x minus y. So get x minus y over x plus y cubed. Let's do the derivative. Let's do fxy the more normal way. Let's do it as the partial with respect to y of fx using the quotient rule, everybody's favorite rule, or not. So bottom, derivative of the top, which is 1 minus the top times the derivative of the bottom, which is 2 times my stuff to the first times the derivative of my stuff. The derivative of x plus y is 0 plus 1, because again, we're differentiating with respect to y. You always have to think, oh, y is my variable, x is 5. It's a constant. Divided by x plus y cubed. Sorry, x plus y to the 4th. Woo. Okay. So we can factor out an x plus y from the top. Left with x plus y minus 2y. Over x plus y to the 4th. Cancel an x plus y and x plus y. And you're left with, oh, look, x minus y over x plus y cubed. It's the same, just like we knew it. So, I cannot stress enough, when you are doing a partial derivative, you really, really, really just have to pretend that the other variable or variables are just constants. When I'm doing this, like when I'm doing fxy of y over x plus y squared, I am really in my head actually pretending. Oh, sorry, that's not the right. I erased the wrong thing. Sorry. And when I was doing this problem, I was like, oh, x is just 6. And the derivative of y over 6 plus y squared is bottom 6 plus y squared times the derivative of the top minus the top times the derivative of the bottom. Okay, the derivative of 6 plus y squared is 2 times 6 plus y times the derivative of 6 plus y, which is 1 over 6 plus y squared. Right? I'm really just pretending that x is a constant, like 6 or whatever number happens to work for you. So partial with respect to y, pretend x is a constant. partial with respect to, I guess we did, I guess I'll write it, partial with respect to x, pretend that y is a constant. Yeah. So you can also do this for functions of more than two variables, which is the pen I haven't been using. So it's the warm one. Okay, that one. Try to not use up one pen right away. As I believe all of these functions I've been writing, I would also be thinking of as, since they're functions of x and y, I'd be like, oh, this is z equals a function of x and y. But you can have functions of multiple variables, I should say, more than two variables, like f of x, y, z equal to, I don't know, something crazy like x squared sine of 2y plus 3z. And then you can find all sorts of partial derivatives. So fx is just 2x times your constant. Derivative of a function times a constant is the derivative of that function times the constant. Okay, fy. Now this is a constant, and I've got a constant times sine of a function. Okay, so the derivative of a constant times a function is that constant times the derivative of that function. What's the derivative of sine of some stuff? It is cosine of your stuff times the derivative of your stuff. Okay, help me out. What's the derivative of 2y plus 3z? You should only have to type one thing, one character. It's 2. All right, the derivative of 2y plus 3z with respect to y is 2 times 1 plus 3 times 0. Derivative of z is 0. And then in a similar way, fz would be x squared times cosine of 2y plus 3z times 3. Because now we're doing the partial with respect to z. Constant multiple hangs out. Derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff, and the derivative of the stuff is 0 plus 3. Ooh, God, there's some interesting implicit stuff too. Let me do one more thing. We got time. We got time. He said, "Does he run out of time?" So what do I want to say here? Let's say we have that x squared plus y squared plus z squared equals 3xyz. And we can't find it explicitly, but we are, well, in fact, let's just say it this way. So we want to find del z, del y. And what we're saying here is that z implicitly is a function of x and y. Right, I can't really solve for z here. Right, z squared, it's going to be kind of big. It might be possible, I don't want to though. I don't need to. So what I'm going to do is I'm going to define del z, del y. I'm going to differentiate the whole thing with respect to y. So here's what we need to know. X doesn't depend on y. Y for sure depends on y. And z implicitly is a function of y, x and y. So z also depends on y. So let's find the derivative. Yeah, sure. The notes say del z, del x. I'm going to do del z, del y. So what's the derivative of x squared? 0. What's the derivative of y squared? 2y. What's the derivative of z squared? Well, z depends on y. So z is like, right, z is some stuff. The derivative of z squared is 2z times del z, del y. Right, the derivative of some stuff squared is 2 times your stuff times the derivative of your stuff. Equals, ooh, I gotta use the product rule here. I have a constant 3x times yz. So I'm gonna get 3x times the derivative of yz is, so the derivative of y is 1 times, derivative of y is what? Derivative of y is 1 times the not derivative of z plus the not derivative of y times the derivative of z. The derivative of z is the derivative of z. Now we're going to solve for the derivative of z. I probably need to distribute this 3x. So I've got 2y plus 2z. I might write this as zy just because it takes less writing instead of writing del z del y equals 3xz plus 3xy zy. I want these terms on the same side. So I'm going to factor out the zy as well. I have zy times 2z minus 3xy equal to 3xz minus 2y, and then divide by this to get zy or del z del x del y, equals 3xz minus 2y divided by 2z minus 3xy. Good times. Interesting.